Hello everyone. So in the last class we were trying to get to how to construct temperature composition phase diagrams, and in that process we first said at any given temperature I have so many phases that are available and I have to look at the so which phase wins in what composition range, right. So that's the first exercise we did, and so depending on the free energy curves we said it's not just alpha phase or beta phase, we should also look at alpha at a particular composition, beta at a particular composition, both of them are in equilibrium as a mixture, so that comes as a competitor to both just a pure alpha phase and a pure beta phase, right. So for example we said, we gave this example, so alpha phase has a free energy curve like shown in green, beta phase has a free energy curve like shown in blue. So from 0 to x2 alpha, alpha is stable, but from x2 alpha to x2 beta, the alpha plus beta becomes stable, where alpha has a composition of x2 alpha, beta has a composition of x2 beta, right. So what does that mean? That means that the number of, or the I mean it's composition, what else can I say. So the atomic fraction of two atoms in alpha is x2 alpha. The excess x2 alpha, so some of the so let's say I am somewhere here, I am supposed to be here, right. So this is my average composition x2, right. So some of the two atoms, they go from alpha phase to beta phase, right. So it is no longer a single phase. Let's say how do you interpret this, right. So let us say I have so this is alpha, this is beta, right. So I am somewhere here, I have forcefully or jabardasti I wanted to stabilize the let's say on the composition diagram. So this is x2, this is my common tangent, this is x2 alpha, this is x2 beta, right. So I am somewhere at this point, let's say, and I have somehow stabilized the alpha phase. So that is the x2 starting x2 0, right. So x2 at time t equal to 0 is this, right. So then what happens is, initially I start with a homogeneous composition of alpha phase, right. So and that homogeneous composition is x2 0, and then so as time progresses, this is not the equilibrium state, or this is not the stable state at this temperature. So what is the stable state at this temperature? The stable state is somewhere here. And what is this state? This state is actually F1 alpha and F2 beta, right. And alpha has a composition of x2 alpha and beta has a composition of x2 beta. So essentially this homogeneous state is going to homogeneous alpha, right. So as time progresses, the homogeneous alpha, that is an assumption, right. So let us say at time t equal to 0 I force the system to be in alpha state, right. It is possible through several means, right. So I suddenly increase the temperature, it is in alpha state, and I suddenly increase the temperature so that alpha is no longer stable, okay. And then what happens is, okay, so so from the alpha, right, so where I have composition of x2 0 everywhere, some of these two atoms start going and nucleating a beta phase, right. And so there will be many such beta phases, but beta phase is rich in 2. So beta phase has a composition of x2 beta. So since some of the two atoms are going into beta phase, the alpha phase that remains has a composition of x2 alpha, okay. Then you may ask the question, what is the fraction of beta phase? That forms, right. Now I am not telling you where exactly beta phase is. Beta phase can be like this, right. So one full chunk right. This is alpha, this is one full beta, or beta can be a little bit of many chunks. This is alpha, this is beta, or beta can be some sort of not just circular or spherical particles, but beta can be some kind of needles or some dendrites or whatever it is, right. So, I do not exactly know how beta is, but I know what is the phase fraction of beta, right. And how do I get the phase fraction of beta? The phase fraction of beta right. I start here, right. So, you can see this is just mass conservation. So, the amount of beta phase or f of beta there is equal to, I am going to call this entire thing as L, right. So, the length of this in composition space x2 beta minus x2 alpha, whereas this is going to be L1, this is going to be L2, or L1 and L2. Okay. So, f of beta is going to be L2 by L, and L2 by L is nothing but x2 beta minus x2 0 divided by x2 beta minus x2 alpha, right. So, this is the fraction of beta. This is called the lever rule. Okay. So, okay, so let me again draw it just for the sake of So, at this point, right. So, I am asking the question, until this point I just have alpha phase, from here to here it is the alpha plus beta phase that is stable, right. But then the question is, what is the fraction of alpha phase and what is the fraction of beta phase in this inhomogeneously looking compound material, right. And here I have only beta phase that is stable, right. So, so the fraction of alpha phase or fraction of beta phase as per thermodynamics is so if this is x2 0, this is x2 alpha, this is x2 beta, this is given by what is called the lever rule. I take this lever and then I divide by the total sorry, that is the fraction of alpha. Okay. So, fraction of alpha is this lever divided by the total length, right. So, that lever is x2 beta minus x2 0 divided by total length is x2 beta minus x2 alpha. Okay. Similarly, f of beta will be this lever, right. So, L1 by L. Right. So, what I wrote earlier is actually wrong. So, this is actually not f beta, this is f alpha. Okay. Yeah. So, that is equal to x2 0 minus x2 alpha divided by x2 beta minus x2 alpha. This is the total length of the lever and this is the part of the lever that contributes to the beta phase. Okay. Now, this is what is called the lever rule. Okay. Now, let us just so we are moving again, let me just draw different colors, then it looks better. So, this is alpha, this is beta, this is alpha, this is beta, right, and then so until here we said this is alpha, from here to here this is alpha plus beta, right. So, here it is going to be beta phase that is stable, right. So, in this composition range, that is okay. So, let us say I am going in this direction, somehow I am putting in more and more atoms of 2 into my system, right. So, there is an alpha phase initially, I keep on adding more and more atoms. Alpha phase is at this composition, right. So, this is x2 0 to start with, okay, and then I keep on, as time progresses, right, just like in any growth process, I supply, right, more of 2 atoms, right. So, more of palladium atoms to platinum, let us say, okay. So, okay, initially I have 100% alpha until the composition gets to x2 of alpha, until x2 equal to x2 of alpha, right. When x2 just exceeds x2 of alpha, right. So, x2 is just greater than x2 of alpha, then beta phase nucleates, right. Now, if it is just greater and I ask you the question what is the fraction of beta phase, you can use the lever rule, right, and then say fraction of beta phase so that just gets nucleated is x what is it, x2 0 minus x2 alpha or so this x2 0 is different from that x2 0, right. So I am going to say I start with I said this is okay. So I start with a composition of x2 1, let us say, okay. So but here once it goes so just above this, right. So I am going into a composition of x2 0, right. That is the total composition to start with. I have flushed in enough 2 atoms that the composition has increased from x2 1 to x2 0, let us say, okay. And so at x2 0 it should precipitate out beta, right. So it should precipitate out beta, this is called precipitation. At x2 0, x2 alpha, at x2 equal to x2 alpha, beta phase should precipitate out. Right, and the fraction of beta phase that just got precipitated will be x2 0 minus x2 alpha divided by x2 beta minus x2 alpha, right. Now this if x2 0 is very close to x2 alpha is a quantity almost equal to 0, right. So initially there is not much beta phase, initially when x2 is just greater than x2 alpha, so fraction of beta is almost close to 0, there will be a few nuclei that are forming here and here, right. So then I increase the flux of 2, okay. By increasing the flux of 2 I am actually shifting the lever, right. So shifting the midpoint or shifting the equilibrium point of the lever, right. So I am moving from here to here to here to here to here and so on, I am moving along this direction, right. So once I move along this direction I am increasing this lever, right. So the beta phase fraction starts to increase, right. So that is simple to see. So then I increase the flux of 2, then the beta phase fraction starts to increase until x2 0 equal to x2 beta, right, or x2 not 0 anymore, right. So this is at another time, but x2 equal to x2 beta. I keep on increasing the 2 atoms such that x2 equal to x2 beta, then your compound, your material which has started with complete alpha, right, at x2 just greater than x2 alpha I will have some little beta phases here, right. So here, right. So this is beta phase, very small quantity of beta phase, right. So almost 0 if I actually compare to alpha phase, and at x2 somewhere in the midpoint, x2 alpha, x2 beta, but somewhere in the midpoint, right. So then I will have alpha, right, some beta here, some beta here, right. So significant amount of beta has already formed, and when x2 equal to x2 beta, then I have very little alpha phase. So this is my alpha phase now and the rest is beta, right. So beta engulfs the material, right. And when x2 is greater than x2 beta, then so it is completely beta, complete full beta, f of beta equal to 1. Okay. So this is how it so I interpret this phase so this G versus X phase diagram, right. All right, and then so in the process we have also introduced what is called the lever rule. Lever rule helps me understand the fraction, right, helps understand the fraction of precipitated phase in the matrix, right. So so it is nothing to do with the composition, right. So, this is phase fraction. Again, these are different ideas. It is easy to get confused. It can get easily confusing, but this is the phase fraction. I have two phases, alpha and beta, and Liver rule tells me what is f of alpha, what is f of beta, right. But the composition in alpha is x2 alpha or something about x2, that is different, right. So, composition in beta is x2 beta, right. So, this composition is something different, right. So, I am not looking at x1 x2 x1 plus x2 equal to 1, I am not looking at the species, right. So, I am looking at the phase fractions. I already know that this part is in this crystal structure, this part is in this crystal structure, I have a phase mixture, and so what is the phase fraction of alpha, what is the phase fraction of beta, okay. The other fraction that we are using is the composition, but composition tells me how much of species 1 is in phase alpha, right. So, phase alpha has an composition of x2 alpha, means there are so it is number of so it is just x2 alpha means number of 2 atoms in alpha divided by total number of atoms in alpha, right. So, number of 1 atoms in alpha plus number of 2 atoms in alpha, this is x2 alpha. This has got nothing to do with phase fraction, got nothing to do with phase fraction, because I see a lot of confusion floating around in confusing phase fractions with atomic fractions and so on, and mostly the confusion arises because we write things like this, right. So, mu 1 is for the species, alpha is for the phase, and then it is easy to get confused because I am using both species and the phase in the same variable. So, it can get confusing, right. So, remember that, right. So, always this is the phase, this is the compound, this is the component, and then when I say x2 I mean the composition which is just related to the component, and when I say alpha or f of alpha or f of beta, that is what I mean as phase fraction, and this is given by Liver rule. Okay. So, all these things are so if you just understand it and if you keep looking at it, you will remember. Okay. All right. So, having said that, let me give you a slightly more complex so it is not just alpha and beta phases that exist, but I have alpha, beta, gamma, delta, right, and at any given temperature they all stack up like this, right. So, so let me draw different colors. This is G of alpha, right, this is G of beta, let me use this color and say this is G of gamma, right, and let me use the black some other color, right. So, this color and say that this is G of delta, okay. So, this is G of delta. I think these are all different colors, I myself can see them differently, but yeah. So, there are all different colors, and so if I ask you, okay, which phase is this is x2, this is just the value of G, okay. So, this is at a given temperature again. I have 4 phases, right. Now, what composition range, which phase is stable? So, we will do a trick of so let me use the orange pen, right. So, we will do a trick again. So, until there, right. So, and then I have a common tangent, and then I have this common tangent, and then this phase is stable, okay. So, until here I have an alpha phase that is stable. Until here I have this is alpha plus beta that wins globally. This is the global stability diagram, what this is called. From here to here I have, actually it is not alpha plus beta anymore, but it is beta plus gamma, right. So, here I have a phase boundary alpha plus beta. Here I have a triple point where alpha, beta, gamma everything exists, right. That is at this boundary, right. So, we will look at that. So, this is a triple point, this is a unique point. Here I will get a phase boundary in a phase diagram if I change the temperature, that is, okay. And then so I have the gamma phase that is stable here, right. I had 4 phases, right. So, I had delta also. So, what is happening to delta? Now, thermodynamics does not care about delta, does not say delta is an equilibrium phase or delta wins at any composition, right. So, because the g of delta is always larger than some other g. It can be g of alpha plus beta, it can be g of beta plus gamma, it can be g of gamma, g of alpha, whatever is the recipe, right. So, always one of these is going to win over delta, right. So, delta is not something that I will see if I do the process thermodynamically, right. So, a very slow process for a long time and then I let the system stabilize, give enough time for enough time and temperature for the diffusion kinetics to happen, right. So, then I will just see so depending on composition range, thermodynamics just says that if you do this long enough, according to thermodynamics the equilibrium phases are alpha, alpha plus beta, beta plus gamma, gamma, these are the most stable phases, right. So, these are the most stable phases. Actually so I realize that I am just using stability and equilibrium sort of without paying much attention. Stability has its own meaning, right. But yeah, so these are the most globally stable phases, what are called globally stable phases, which is what thermodynamics predicts will occur. Okay. Whereas this is also a stable phase, but to get to delta, however, we have to do some tricks. We should to get to delta, which is also a stable phase. Why am I saying it is a stable phase? Because if I see g of delta has a curvature which is positive, right. So, it has a positive curvature, right, and it turns out that if dou square g by dou x square that is positive, then that phase is stable. Whether it will win or not, whether it is globally stable or not is a different question. It will win or not in comparison with other phases. Is a different question, right. But it is a stable phase, this is stable, that is okay, but it is not globally stable, right, which means there is some other phase. Globally stable phases are astable, which means their dou 2 g by dou x 2 is greater than 0, their curvature is greater than 0 at that x 2, right, and the g of x 2, right. So, of that particular phase is the lowest, right. So, I have a few phases, right. So, GP1, GP2, so GP1 is the lowest, then P1 is called the globally stable phase, right. So, here one constraint is satisfied in case of delta, g of dou g delta by dou x 2 square that is greater than 0 at whatever x 2 I take, but g delta x 2 is never the lowest, always something else wins, right. So, such phases, the delta phase, right. So, such phases are called metastable phases, right, which means there is something else that will win. If you give it enough kinetics, it will eventually go to some other phase, right, but you can sort of trap the system. This is not thermodynamics says given infinite time, infinite diffusion kinetics etc., delta phase is not a stable phase, right, but you can trap the system in these locally stable phases or in these metastable phases, right. So, if I heat it fast or so if I cool it fast, right. So, I take it to certain temperature and then I suddenly cool it, right. So, then I can get to phases like what are called delta phases, right, or so I can do things like I can nanostructure materials. By nanostructuring so I take help of surfaces, stresses, right. and so by taking help of surfaces and stresses I can get to these I can stabilize the metastable phases. Right, or let us say so there is a metastable phase, a delta phase, which has a structure like this. This is the delta phase structure, right. Sorry, let me draw it in a slightly different fashion. So it is somewhat like this. So it is some kind of a sheared phase, right. So I have sheared this nanoparticle somehow and I get to this delta phase. Okay. Now it has to come back to some other stable phase, and that stable phase is somewhat like this. Let us say this is the stable phase, right. So somehow over time this should unshear itself. There is some shear that somehow the surface is stabilizing this shear. Over time the material should unshear itself. To go to a stable phase, okay, a globally stable phase. Okay. Now another example, right. So in this metastable phase, so let us say there is some elements like this, right, and so some other interstitial is coming and sitting here. So this is some this is iron, let us say, this is carbon, this is iron, this is carbon, this is iron, this is carbon, right, this is iron, this is carbon. No, I want to give you an example of diffusion. I was just giving you all diffusionless transitions examples, but let us say yeah. So let us say I have a material which is indium, so this is indium, or okay. So let us not worry about exact material, A, right. Then I have B, then I have A again, and so on, right. Now this is a metastable state. This ordering is just because of some kind of kinetic trapping. Or sorry, let's okay, let me give you this example. Yes, this is a most famous example that I keep giving. So there is what is called so I heat up a material, right. So there is a material called germanium antimony telluride, right. So Ge2Sb2Te5, right. This is the same material that is used on your CDs and DVDs, right, as an active material. This material can exist in two phases. So GST, I am going to call it GST, can exist in a crystalline phase where there is order, and amorphous phase. Okay. So along the C axis, okay, so I have a plane filled with tellurium, then germanium atoms, then tellurium atoms again, then antimony atoms, then tellurium atoms, then again antimony atoms, then tellurium atoms, then again germanium and tellurium, right. So this is a 9-layered compound, right, and then I will have the second 9 layer starting and they start with tellurium again, and the same stack continues. So tellurium, germanium, tellurium, antimony, tellurium, and so on, right. So and this continues, right. So in the C axis this is how they arrange themselves, and so here I have so this is a long bond, and here I am bonding between tellurium and tellurium, right. So, this is a weak bond. The bond between tellurium and tellurium is a weak bond and it is a van der Waals bond, right. Whereas, bond between germanium and tellurium or antimony and tellurium, these are more covalent or ionic bonds, right. So, germanium, tellurium, antimony, tellurium, these are more like covalent bonds, right. But tellurium is a weak bond. As a result, this becomes, this becomes this GST becomes a layered material, right. Layered material meaning after every 9 layers I have a van der Waals gap, and then 9 layers and then I have van der Waals gap, and then 9 layers and then I have van der Waals gap, and so on and so forth, right. So, as a result, I can also use Scotch tape and peel off 9 layers, right. So, 9 layers is how much, right. So let us say one so TE to TE will be about 5 angstroms. So, 9 layers will be 5, 5, 5, 5. So, 4 5s are 20 angstroms, that is about 2 nanometers, right. So, I can get to 2 nanometer films just by peeling them off using Scotch tape, right. And someone so if you peel off graphene using Scotch tape, you all know this, and that got a Nobel Prize, right. I mean, it is not this trivial, but so just for joke I can say that so just peeling off graphite so to make graphene using Scotch tape, that is a standard technique now, and that got a Nobel Prize of making materials, the simplest way of making materials, I must say. And you can do the same thing with these GST sort of materials, right. So, GST has, it is a non-nipple layer. I will keep coming back to this material, this is a very interesting material. Now, the interesting part, the other so okay, why do I care about this material? So this exists in this non-nipple layered crystalline phase, right. But then I can actually apply a laser pulse, right. So, this is a crystalline GST, it is a thin film, right. I can apply some kind of a laser pulse, right. So, if I apply laser pulse, it will actually melt this region. So, I am applying a laser pulse with this intensity, right. So, this is pulse intensity versus time, right. So, laser energy is absorbed, the photon energy is absorbed by GST and converts to heat, right. So, light to heat, and this heat will melt GST, right. So, here I have a melted GST, which is a different phase, it is a liquid phase, right. Now, once this pulse is removed, this is removed so this is let us say a nanosecond pulse. So, it is removed, so if this is some 100 nanoseconds, it is removed in 2 nanoseconds, right. And this removing of the pulse also means I am removing the heat, right, suddenly. And if you have a metallurgy background, you are going to call this a quenching process, right. So, when I quench it, so I am melting it and I am quenching it, right. So, when I quench it back to room temperature, right. So, I do not have enough time, right. So, I do not have, so now I am in a liquid phase, right. At high temperatures I am in a liquid phase where so everything is, there is enough free volume, things are moving around, right, and then I suddenly freeze it, by quenching, right. So, then I do not have enough time for atoms to move around and form a nice globally stable crystalline phase, right. So, I suddenly came down to room temperature, and at room temperature atoms do not move much, right. So, so once I remove the pulse, before the material could realize, right. So, it has been frozen to room temperature, right, and at room temperature not much diffusion can happen. So, in some sense I am taking the disordered structure of liquid and freezing it, right. So, what do I get? I get a disordered solid, right. So, the viscosity increases suddenly, right. Some properties like viscosity increase, but it does not have enough time to reorganize itself, because there is no time for atoms to reorganize, right. And as a result, so what I get is what is called an amorphous phase, right. It is a disordered phase, there is no crystallinity, no long range order. Periodicity, right. So, no long range order in this amorphous phase. So, I can take GST, which is so if I look at that temperature, right. So, at room temperature, if I look at G of the crystalline GST, right, that is actually less than G of amorphous GST, right. So, now amorphous phase is formed because I am not giving it enough time for atoms to diffuse around and come back to the crystalline phase, right. So, although G of amorphous phase is larger than G of crystalline phase, which means amorphous phase is a metastable phase. And how do I know it is metastable? Because I sort of know that dou square G by dou x2 square is greater than 0, the curvature is greater than 0, but it forms, right. It forms, and then so I have to actually for it to go back to crystalline phase, I have to heat it a bit. It forms because so there is no time to form the crystalline phase, no time and diffusion at room temperature to form the crystalline phase, right. Now, how can I form the if I really want to form the crystalline phase, then I give another laser pulse, right. This time this laser pulse is going to heat the material to beyond temperature is greater than crystallization temperature, right. Now, when the temperature is beyond the crystallization temperature, then these atoms in the amorphous phase, it does not need to be beyond melting temperature, it is beyond the crystallization temperature, then these atoms start to reorganize, starting to form these planes of germanium, antimony, these nonaples and so on and so forth, then it forms a crystal, right. So, at high temperatures, at higher temperatures, T greater than Tc, which is called the crystallization temperature, there is enough diffusion kinetics for the globally stable phase to form, right, and the globally stable phase is crystalline phase. Okay. Now, imagine that so this is a technologically relevant material, right. So, because you have, I do not know if you guys are old enough to have used CDs and DVDs, but this is exactly the same material on CDs and DVDs, and if I have to on a DVD disc, right. So, there is a thin film of GST, right, and on this GST I am going to say this is amorphous, this is crystalline, this is amorphous, this is crystalline, 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 amorphous, and so on. I am going to write all these bits, right, and all these bits so they have different reflectivity, right. So, amorphous has a reflectivity, a smaller reflectivity, crystalline has a larger reflectivity, and when I read it, using what is called a reading laser pulse. I am going to read 1 1 0 0 1 0 0 0 and so on and so forth, right. I am going to read a set of binary digits, right. So, as a result this is a memory that has stored some data, and then when I actually play it, when I convert it and play it, I am going to watch a movie, right. So, I am going to watch some Rajnikant movie, let us say, right. So, I am going to watch Basha. Okay. So, this is how I used to watch movies using DVDs, right. The technology is simple. Okay. Now, the idea is when I amorphized, when I have written the bit in an amorphous phase at room temperature, it is stable. I mean for all practical purposes, right. So, it stays as an amorphous phase because there is no kinetics to form the crystalline phase, right. So, it is not that metastable phases cannot exist, they cannot exist infinitely. If I leave this CD infinitely long, right. So, over 50,000 years or something like that, right. So, until the next transformation of human beings comes, next evolution of human beings comes, then maybe something will change, that is what thermodynamics is saying, right. But for all practical purposes I can still use metastable phases. I know how to create it, right. So, I have quenched the liquid to form this metastable amorphous phase, and at room temperature I can use it as a nice memory element, right. So, I can write 1 and 0. 1 being the crystalline phase and 0 being the amorphous phase. Crystalline phase is globally stable phase. Even after 50,000 years it will stay as crystalline phase, right. But the amorphous phase maybe after 50,000 years will convert to a crystalline phase, but that is okay because I am going to use a CD or a DVD for hardly so nowadays I do not even use it. So, whatever I used in my childhood is now thrown away, okay. So, so it is not that metastable phases cannot exist. In fact, all the beautiful material science, right. So, if I want to make good memories and other things, I bank on the metastable phases. Stable phases are more boring, right. So, I want to get to metastable phase and get out of it, right. So, that sort of a thing, and that is interesting for electronic functions, okay. So, this amorphous phase being one of the metastable phases, right. So, there is a globally stable phase, but so at room temperature I can prevent it from happening in a reasonable time scale of 10 years or something like that, right. So, even so I can use this also as a RAM, this is called PC RAM, phase change random access memory, right. So, in a RAM instead of using laser pulses I am using electrical pulses, right. So, I use an electrical pulse to write or to melt a bit, right. So, a crystalline bit into an amorphous bit, and then so I can then apply another electric pulse to actually heat the amorphous bit to a crystalline bit, right. So, I can heat, melt and quench, that is how I form the amorphous bit, and heat beyond the crystallization temperature, that is how I form the crystalline bit, right. So, I can do everything electrically. If I do everything electrically I can use it as a memory, right. So, in fact these materials are used as cache memories inside your computers, right. So, Intel has started using them as some level of cache memory inside your computers, okay. So, these are called phase change materials, and the way I am switching from 1 and 0 is between a stable phase and a metastable phase. I can also switch between two metastable phases, that is fine, right. But if I am switching, if I am in the switching business, the memory business, metastable phases are my friends, right. Although they have this thermodynamics says, oh no, you can never form them, that is not true, right. So, kinetically I can trap them in the metastable phase without giving it enough diffusion kinetics, and then things become interesting. Only when I need it I will increase the temperature so that it goes to a stable phase, and then I know how to come back from a stable phase back to a metastable phase. So, I am going to use it, right. So, so it is not that some metastable phases are somehow thermodynamically some outcast phases, they are the more useful phases, okay. So, for me. So, with that let us conclude this lecture, and then I will again meet you in the next lecture, and we will continue on this thread of phase transitions. Thank you very much.